continue from our previous lecture, where we discussed broadly the applications of a technique, point partitioning technique called WSPD, or well separated pair decomposition. And today let me try to sketch the algorithms or the kind of algorithms people use to construct a WSPD, or to be more accurate, we are looking at epsilon WSPD. So, the construction actually proceeds from a very simple structure called quadtrees. Okay. Now, we never took up quadtrees in this course, not yet, because quadtrees usually do not have any provable properties. Normally, the kind of quadtrees people use in practice, and it's a very popular data structure, namely that you're given a set of points let us say on a plane, then you enclose that in some kind of a square, an enclosing square. Okay. And then you partition the point sets repeatedly by the 4 sub squares, which are half the size of the original square. All right. And you continue this partitioning okay, let me take just one square. So, now of course, when you have done this partition, the second level of nesting, these are empty squares, right. So, you do not need to partition them any further, right. So, you are going to only partition those squares that contain some point, not So, I am going to continue partitioning here, okay. And then of course, now when you have one point in a particular square, you can kind of stop partitioning, because your purpose is served. That is, you want to get it down to either a constant number of points or a single point, whichever termination condition you prefer. And then this structure, okay, this partitioning structure can be easily stored in a tree, where the root denotes the bounding square. Okay. So, let me use square to denote that, and then there are the 4 children corresponding to the 4 sub squares, right. So, call it okay. So, then you have these 4 squares corresponding to the 4 partitions, okay. And then I have subdivided it further, okay, and 2 of them basically they are leaf nodes kind of. So, they terminate, and then the other 2 we partition, and then again subsequently they terminate, right. So, we go to the next level, again we have 2 leaf nodes, okay. Maybe I should make them green, okay. And then we have only one point in these 2, and we do not do anything further. We kind of again we can say that they are done. So, you continue this partitioning for all the 4 subsquares recursively, and this tree basically corresponds to the partitioning that we have described, which is essentially a quad tree. Okay. So, this tree is called a quad tree. Why? Because analogous to the binary tree, it has a maximum of 4 nodes, 4 children at any internal node. Okay. And actually, this quad tree, has it. I mean, if you think about the one dimensional quad tree, it is going to be an interval where you are going to bisect the interval in terms of its length. Okay. So, here we are always partitioning in terms of the length of the square rather than the way the points are distributed. Okay. And therefore, as I just remarked that the you do not have many desirable provable properties for quadtrees, and in particular you could have a distribution where of course I start with a square, but then I may have most points clustered in here. So, I am going to basically generate lots of, but in fact, this could be much smaller. So, I have to go deep and deep to basically somehow split this point. So, the whole idea is that I have some point sets and I want to separate them, right. I want to separate them till my partitions become small, like 1 point or just a constant number of points. But there is no guarantee, because I am actually doing the splitting based on the side of the square rather than the way the points are distributed. Okay. This is precisely why so far in the course we did not talk about quadtrees. We are always talking about dividing the point set using a median line. This is very different from the median line. This is the median of the interval. It is not the median of the point set. Right. And therefore, what can you say even about the most basic parameter of a tree, that is what is the height of a quadtree. I could of course start with just to make things bad, I could have a point in the corner, so that I am forced to have this bounding square, that is fine. Thereafter I basically have everything clustered towards one corner. So, I have to keep splitting it, how many times do you have to split it? Do you have any bound on that? Yeah, right. Yeah, what we described in the last lecture, it is kind of the spread, I mean that is going to describe that going to define the height. Okay. So, yes, I mean that is a good thing to observe, that log of the spread. Okay. We have defined the spread in the last class, the ratio of the maximum distance to the minimum distance. But then what is the bound on that? It is not a bound based on the number of points, it is something that has got to do with the values associated with the coordinates. Okay. And now, depending on the model of computation, you may or may not have a bound. If you are working with a bit model, then you can say, okay, my input had size n, so no number can exceed, let us say, n bits or whatever, and then the smallest number can be 2 to the power, the largest number can be 2 to the power n, the smallest number can be constant. So, the ratio is at least 2 to the power n, okay, and log of that is n. So, at least in that kind of a computational model you have some bound. In the model that we have been following so far, that is real number, no bounds basically. What bounds do we have? I mean, if every input is a real number, it can be arbitrary. Right? So, therefore, even if you can't even get a bound on the height of this tree, how do we, why should we use this tree? I mean, at least in computer science, it is not something that we look for. Right? So, we will have to do something to modify this, not the definition, but the way we look upon quadtrees. Right? Okay. So, the first thing that we do is we define the notion of a canonical quadtree. What is a canonical quadtree? So, in the previous diagram, we simply just took this bounding square, okay, and the bounding square could be something arbitrary, let us say some 0 to not 0, something anything arbitrary, let us say some alpha and beta. Okay. Now, if we specify that the alpha and beta can only take some forms. Okay. So, for instance, we want to always start with alpha equal to 0. Okay. Then and we want beta to be, let us say, power of 2. Okay. So, what I am defining is something like a grid. Okay. So, if you have grid points, so if grid points have some specific value, say powers of 2. Why powers of 2? Because then it is also easy for us to divide, right. It is just exactly division by 2 is very simple. Okay. Then it is some kind of canonical grid. Okay. And we want to align our quad tree with such grids, such a family of grids. So, let us say G's of I, okay, is basically looking at the points corresponding to G3 I are 0, 2 to the I, 2 times 2 to the I, and so on and so forth. So, that is what I am calling G's of I. So, G's of 1 is 0, 2, 4, 8, and so on and so forth. G's of 2 will be again 2 to the power. Okay, so am I writing it? Yeah, so that kind of thing. So G's of 1 would be, so these are spaced basically 2 apart. But those are the coordinates, so everything is spaced 2 apart, right? And G's of 2 will be the 4 apart, right? This and this. So every alternate will be the G's of 2. Okay, G's of 3 will be again 2 of these will form. So you are now getting basically G's of this way. What is the advantage? Your G's of I, okay, basically is a subset of G's of j, where j is less than I, right. So that is okay. When it's going to save some cumbersome computations if we have these grids always that way. So when we halve them, okay, it falls. We have some predefined kind of grid points. Right? It still hasn't quite solved our problem that we are facing in terms of bounding the height, etc. But this is kind of the beginning of that. So in fact, what will work with the more standard thing to work with, or some authors prefer that instead of looking at G I, we look at actually. So G's of I is defined as the grid points 1 over 2 to the power I rather than 2 to the power I. So you take the maximum square to be like unit square and then you just half it. Okay. So instead of looking at 2 to the power I, we look at the 1 over 2 to the power I grid. So the overall square will be, let us say, the unit square bounds everything, okay, and then we partition it into the G half and then the G 1/4 and so on and so forth. Okay, so what's a very simple application of these this, well, I mean just the quadtrees, not just the canonical quadtrees, but quadtrees. We could have we could do, let us say, some kind of point location based on that, right. I mean, we have studied so many things about point location where we have strict bounds, linear space, order log n time, and so on and so forth. But just the trivial idea where you have a map, okay. So let us say the vertical ray shooting query or something. Okay. So I again have the map. This is the map, then I overlay it with the grid. Okay. And I do the same thing basically, I keep subdividing it. Okay. And what do I keep track of? I keep track of which segments intersects which subsquares, right. So, we have this family of grids, and when we have to do the point location, okay. So, well, again it fits very well with our notion of range searching or point location, that where when we do basically some kind of refinement. Okay. My point is, let's suppose I get my point here. Okay. So, if my point lies in this square subsquare, okay, I only need to look at those line segments that intersect this subsquare, and we keep refining it till we come to a point where in that subsquare. So, as we keep refining it, of course, this is not a nice example. So, let us say somewhere here. Okay. So, we will keep refining it till we have only a constant number of segments intersecting a square, then we can do the straightforward vertical reshooting and find out what intersects. Okay. But what is the drawback of this scheme? I mean, yeah, we do not really have a bound on the either the height of the quadtree, which is the query. So, query is what? The query is the height of quadtree, right, on which we do not have a bound, okay. And the space also we do not have, since we do not have a bound on the height of the quadtree. A line segment can basically keep intersecting the subsquares over the entire depth of the tree. So, again this is also kind of unbounded. So, both of them at this point, although the scheme is kind of tempting to use, but provable bounds will be hard to obtain just with this kind of limitation. Okay. So, yes, I mean these kind of quadtrees have been in practice for about maybe 20-30 years, even probably before the computational geometry sort of emerged as a rigorous discipline. So, quadtrees have been used, people do use quadtrees. So, I can't wish it away that saying that this does not work. It certainly works in practice, and therefore, people keep using it, and of course, it is kind of easy to implement. So, this could be a potential this could be a simple application of quadtree. Okay. Now, one way we can try to somehow have some kind of control on the height, okay, and in this kind of pathological case where points lie in one corner, okay, is by actually doing something to the structure of the quadtree. And what is that? So, you have all points, let us say, concentrated in one corner, or most points, and only a few points are here and there. So, that you are forced to start with a large bounding square, and you are going down the tree. Now, most of the let us say the subsquares are going to be empty. Okay. So, what it essentially means is that in that tree you are falling, this subsquare contains something, only one of the subsquares contains something, and then one of its subsquares contains something. So, you have a long skinny tree essentially, right. You have a long skinny tree, and in that long skinny tree maybe you do not basically have anything. I mean just the subsquares are contain one subsquare as a child. So, this entire path you may want to compress. If you have just one child of a node, you may just want to compress, so that when you compress, you do not have to go through a long path to reach some meaningful stage where the points are actually going to be partitioned. Okay. Before that, no points are actually partitioned. You are simply just following the subsquare of a subsquare of a subsquare. Okay. So, you can try to compress that path. So, that is one easy observation. So, to do something to the structure of the quadtree. Okay. So, one observation is compress the nodes having only one child. Okay. So, what looks like this, and then maybe you have some there is some bifurcation there. So, this entire path I can compress to, so suppose this node is V1 and this node is V2, I can directly hang V2 on V and forget about this. Now, in that process I have done one damage. What is the damage that I may have done? When I go to the node, the original quadtree, I go to a node of the quadtree, I know that it is exactly sort of a square, let us say it is an aligned square, it is exactly half of the size of the thing. Now, here when I have compressed let us say a path of 5, 6, 7 trees, it is no longer that case. So, I have to somehow find a way to identify that V2 and V1 are related. Of course, the pointers will give us that. Now, besides the pointer, there is one more property of this aligned quadtree. So, I did not quite spell out everything. So, let me just write it out. So, what one of the advantages of an aligned quadtree is that I can store the quadtree not as a tree, but actually, can you say something? In what kind of data structure? We are searching, right. So, what other kind of structures that can we use? Trees are used because we always have a link from the parent to the child, and you can follow those links. What other kind of structure can we use? Skip list will also be some kind of falling pointers. Yeah, some kind of arrays, but what's more specifically what? See, a complete binary tree is never stored as a tree, right? I mean, it is stored in array because implicitly that what is the child of which one. You can just, you don't have to store the pointers. So here suppose I have an aligned quadtree, okay, where I know precisely at depth I. So the advantage of aligned quadtree is that let me just write it out. So one advantage is that at depth I from root we know exactly which subsquares can be present. So corresponding, so what I basically mean, like your complete binary tree structure, okay, I give you two nodes, you can actually tell me whether or not it has the relation of ancestor child, right. The advantage of a complete binary tree is that because you have full levels and so on and so forth, you can map it basically to an array where given two nodes I can in constant amount or some calculation I can immediately tell you that this is actually an ancestor of this node and vice versa. Right. So here also I claim the same property. If they are aligned, okay, and I give you these two nodes, you can quickly tell me, because I know that for the ancestor child relation, it has to be a subsquare of the subsquare of the subsquare. I know exactly how the numbers look and how the grids look, right. And if I can, then what would be a structure to store this? Yeah, hash table. Good. See, the reason why you don't think about a hash table for a complete binary tree is because you have your array of size n, and basically it has about n nodes or n over 2 nodes. Okay. But in this particular case of a quad tree, you may have some subsquare that are empty, you may not want to store it. After a while, you have only one point in a subsquare or an empty subsquare, you don't want to store the children at all. So a priori you have no knowledge about how the things are going to be distributed, okay. But you know that what can you claim about. So once I have eliminated these long paths, okay, what can you claim about the number of nodes of the quad tree, okay. So observation. So this is called a compressed quad tree. Of n points has at most 12. What is that quantity? Log n. No, how can it be log n? I mean, there are n points, right? Okay. Order n. Why is it order n and whatever? No, log n is cannot be right. No, not the height. The height we are not able to do much. I mean, not yet. Right. So, every level points are getting partitioned. So, it has to be partitioned at least, it can be partitioned at most n minus 1 times, right, before it becomes trivial point sets. And you know, these kind of nodes where where you hang it to this one, you know, maybe there is some extra another n node. So, it is certainly no more than order n nodes. Okay. So, we have at least gained something. We can now say that, you know, this kind of a quadtree, a compressed quadtree, has only order n nodes. And moreover, this compressed quadtree, or in fact not just a compressed quadtree, the aligned quadtree, one advantage of, let me things, from this advantage we can claim, just as it was remarked, this can be stored in a hash table. I can hash every square, because I know that every square now is not an arbitrary square, it is an aligned square. Okay. So, it can only have certain kind of coordinates, right. So, I can hash it, right. Can be stored in a hash table.
How do you know after the compression that where the square will be?
No, we don't know. We don't know anything about that. But suppose I am now, let us try to implement a search algorithm. Okay. So, if I am trying to do, basically what am I trying to do? I am trying to find, you know, what kind of. So, if you look at this application, what are we trying to do? We are trying to find that which is the smallest subsquare that contains this point, because the smallest subsquare means that we do not subdivide it any further, because there is no useful information after that, right. Once the subsquare contains only one let us say object or one point, okay, we are not going to subdivide it any further. So, a point location query actually is of the following kind, that which, so point location query which is the smallest square, or let us say, yeah, subsquare, which is basically which grid level, you know, subsquare I largest j for which Gj contains P. So, this is called P. So, a search in this quadtree essentially amounts to which is the smallest square that contains this point. And how are you going to find this? One is that, you know, I just do, you know, from the original bounding box, I go to the child, I go to the child, I go to the child, you know, and if the path length is h, then this would give me a performance of h, right. Height of the quadtree is certainly a bound on the search time, but now that we have been able to hash, I claim that we can do it much faster.
Start from the root.
Yes.
Check if it is it will be present in the root. Then we check the next squares in the sequence, because the root would be hashed to the next child, the first child.
No, no. When we hash it into a table, you know, we are only hashing those squares that are relevant to the quadtree. We are not going to hash anything that is empty, or basically after the leaf node we do not have any children of that. So, we have a certain number of nodes in the hash tree, as in the quadtree, okay, and those, instead of storing in a tree, explicitly a tree with pointers, we are just hashing them, okay. So, that, you know, I can find out, given a node, whether its child exists or not, by simply looking at the whether I will search for that. Every square has a label, let us say, right. Every square has a label, I can label every square. So, every square has a unique address or whatever, and that can be hashed. So, I can always find out if there is a child of a certain node by just checking whether you know, it is present in the hash table. And let us assume, another thing maybe I should warn, or, you know, point out, is that we have a very good hash function where we can do constant time hashing, okay, like essentially the universal hash family. So, we are not talking about some, you know, some you know, modulo kind of hash function. We are talking about a proper hash function, okay. So, by hashing we mean a performance of order n space and order 1 search time. Okay. Example, universal hash family. Okay. So, I hope everyone knows about this, or otherwise I could give you some background material. So, our hashing works very well, it's constant space and it's constant time for search. Okay. So, if I have to search where I don't explicitly have the pointers, I first of all there is some unit square, every point is present. Now, I want to see if there is a certain child, okay. I will find out if that child exists or not. Okay. I can always find out a child will have a particular label. I will just check whether it is present in the hash table or not. In fact, I can find out if a child of a child of a child is present or not, because again everything has a unique label. The quad tree, all the children of the quad tree have some distinct unique labels, right, and I can always find out if a certain node is present or not. Now, given this property, I claim that we can search much faster than actually trying to just go sequentially from the root to the child to the child to the child, again using the hash table, because now we are, instead of following the pointers, we are using the hash table to find out the child of the child. Yeah, right, great. So, you do basically a binary search on the path basically, right. So, can speed up search, speed up point location using binary search on the search path, right. Eventually what we need to find out which is the smallest square that contains this point, right, and I know precisely, okay, if the point is in a certain, so this is my unit square, okay, and as I subdivide further, the second level I know where it is, the third level I know where it is, the fourth level I know where it is. So, it is a question of as I subdivide, I know exactly the nested sequence of squares where the point is going to lie. Okay. You give me a level or a depth, okay, and I know exactly which square, what is the label of the square that is supposed to contain that point. Now, the question is, does that square actually exist in the data structure in the quad tree? So, it is strictly speaking, it is what is called an unbounded search, but the unbounded search can be basically done by using the binary search. What is the smallest subsquare that exists in the hash table containing that point? Okay. Because all the family of the nested squares have distinct labels, right. So, now we immediately, even if we have, let us say, a path length of n, suppose, now see what has happened. So, from the compressed quad tree, we have got it down to a situation where a length of a path is no more than n. How do we actually construct a quad tree? This still does not tell us that a quad tree can be constructed very quickly. We are compressing the quad tree as an after this thing, after processing, right. Here is a quad tree, okay, which someone built somehow, and now we have as an after, is a post processing, we compress the actual quad tree that gave rise to this particular quad tree. We can shrink the paths, we can compress the paths, okay, and then can hash the whole structure. But how do we actually build a quad tree in some reasonable amount of time? Well, for that we have to define some algorithm. Yeah, we want to do that. How do we do it?
Constructing some type of a range searching.
So, still how we get a bound on the height in that case?
Yeah, we do not get a bound. That is the thing, we have to very quickly somehow get a bound on the height. To be able to compress, we need to know that all the things in between do not lead us to anything, right. I mean, the paths of where this is, which is basically a linear path, is basically the trouble spot, right. If we are splitting, then we can charge it every time we split. We can't have more than n minus 1 splits. We can't have more than n minus 1 splits. But then these long skinny paths are the ones that are a problem. So, we somehow need to figure that out quickly in the construction. Every time we have 2 branches, we can charge. Right. So, that turns to be a somewhat tricky thing, but not that much. I mean, Okay. So, what you do is so again the what is the problem? The problem is that okay, so constructing a Quadtree efficiently. Okay. So, again the basic problem is that you may have this is a unit square. Okay. And you know some of these points may be reasonably distributed, but let us say just that we have this trouble spot, okay, which is really sort of small. Okay. So, the number of times have to divide into subsquares is going to be quite large, and that is the path. Those are the paths basically I am worried about, not just one such cluster, but there will be many such small clusters, and those are things that I am worried about. So, the idea is the following, that can we find a subsquare so ISM canonical basically means aligned with the grids. Okay. A canonical subsquare. By the way, whatever I am saying actually goes through in any dimension. Okay. It is just that instead of so in 2 dimensions it is a quadtree, in a 3 dimension it is a 2 by 2 by 2, right. So, it is an octree, and in d dimension it is basically 2 to the power d, basically the number of children will be 2 to the power d. Right. So, but the same arguments and everything goes through. It just but it becomes more and more expensive because you have more children, that is all, but the qualitative arguments all go through. So, can we find a canonical subsquare, okay, that contains a large fraction of the points, where large fraction is a constant fraction of the points, of the n points, let us say. Let us say some alpha n for some constant alpha. Okay. If we could, then we are in good shape. Why? Can you tell me? Well, we don't need, we can't start from there. See, we also have to see it is only a fraction of the points that we have found there is a canonical subsquare that contains a fraction of the points, but there are also points distributed everywhere else in the square. I claim that with this we can devise a recursive algorithm. So, we can look at the points, we can look at the we can look at the subsquare, the canonical subsquare, and the remaining thing, and then what we can do is recursively build the squad tree for this canonical subsquare and for the remaining subsquare minus these points, and paste them together. So, we recursively call the algorithm, that is all. So, in this particular case, let us say here is, of course, the entire cluster we may not be able to cover, but let us say at some level, okay. So, maybe this is the dense subsquare, this is the dense that alpha n points, this particular thing contains the some substantial number of points. Then what we can do is we can take out those points, construct the square. So, let us call this some this is the subsquare, that is the square S prime. Okay. Then what we do is we define a so initially we have to, this is the unit square, okay, and now we devise a quad tree for the original square, okay, minus these points, okay. So, P is the original set of points. So, P minus S prime, let us say, is some quadtree, okay. And for the S prime we have another quadtree, and the S prime is going to hang somewhere from here, from the original one. That we can figure out, because we know exactly which square this is. So, we can attach it. So, this one, this subtree, sorry, this quadtree corresponds to this corresponds to S prime. Okay. This is for alpha n points, sorry, okay. And this is also, actually we have to, this is not enough. So, we have to ensure that this alpha is strictly between some two bounds, it cannot be just all the points are here, then it does not help. So, we need to have bounds both ways. So, this is a subtree corresponding to 1 minus alpha n points, and this is a subtree corresponding to alpha n points. And then we build them all recursively, again using the same idea, that again we will look for a subsquare that contains a substantial number of points. And if we, so what happens, we can write this recurrence to analyze the time bound. Okay, if t's of n is the time to build the this using this algorithm, then it is, we are building basically for t of alpha n plus t's of 1 minus alpha n plus the time that we require to find this dense subsquare. Okay. Turns out that this one, so this becomes a problem on its own. It's a a problem of it is not completely trivial. So, how do you find a subsquare that contains a large fraction of the points? First of all, does such a subsquare exist or not? That is also not clear. Right. So, for that I will pose this problem and leave it as a kind of an exercise for you. Okay. So, I'll make a claim, and the proof of the claim is left as an exercise. So, given a point set P of n points, we can compute a disk D that contains n point, sorry, k points, k is less than or equal to n, and k is a specified parameter, okay, contains k points such that radius of D is less than or equal to 2 times the R opt n D, and I will just R opt, let us say k. I will just define what is R opt k. So, R opt k is the smallest disk that contains k points, exactly k points. So, well, I mean exactly means you do not have let us say some singularity case that all points are on the same coordinate or something like that. So, without singularities. So, think about the smallest disk that contains k points, okay. And this itself is a this is not such a simple problem, okay, but do not conclude that it is an NP-hard problem. It is not an easy problem, but it is not an NP-hard problem either. But what is being said is that we do not even need that optimal smallest radius. We will be fine even if it within a factor of 2 of that, and that will be much easier to find. And if we can find that disk, okay, which is twice that, I claim that we have solved the earlier problem that we have. So, from that disk you can actually carve out some squares. The idea is that from that disk you can carve out a few squares and one of those squares will have a large fraction of points. So, it is like this. So, I have a disk, okay, which has these points and maybe with certain, the disk has a certain radius, let us say d. Okay. So, you can carve out some fixed number of squares, so that one of the squares will certainly have that because all the squares are inside, one of the squares will have a large fraction of the points. Right. And how do you find this, and how quickly can you find this approximate disk? Okay. Okay. D can be found in order using a very simple algorithm. There are many ways of doing it, but I am just stating one of the simplest one. Okay. So, if k is omega n, or let us say alpha n, so this is order n. So, if k is a fixed fraction of n, then the running time is just linear. Right. And if that is so, this one is linear, and then the whole thing is, if alpha is some kind of constant, it will be n log n. Right. So, you can actually build using this method. So, the compressed quadtree. So, claim compressed quadtree, making too many mistakes, can be constructed. Okay. So, let me conclude here today. So, still no sign of the epsilon yet. Okay, we are still not done the epsilon. We are supposed to go from quadtree to the epsilon well separated pair decomposition. So, epsilon has not made any appearance here. So, let me just tell you in one line what we are going to do next time. We will start with a set of points, we will build a compressed quadtree, and from the compressed quadtree we have a very simple algorithm. Simple means simple in terms of describing it is going to be very simple. From where we will build a epsilon WPSD in time, again that is proportional to the number of the pairs that it will output. Okay. So, WPSD outputs some well separated pairs, right. Epsilon WPSD outputs a set of well separated pairs of subsets of points. Okay. And this algorithm, starting from the set of points, will first build a quadtree, and then from there we will build a epsilon WPSD will output those, and it will run in time proportional to the number of pairs. So, the total running time will be the number of pairs that it outputs plus the time to build the quadtree, which is n log n, which means that it is going to be fairly efficient. And there we will find some kind of dependence on the epsilon when we actually build the epsilon WPSD. We will have a dependence like 1 over epsilon to the power d, where d is the dimension.